Now, we are going to do some tutorial problems and then some of them we have already done before, but some more we are going to do here. Simple ones, we will start with simple ones and then we will show some applications for systems of relevance. Once you understand these problems, I think you will be able to understand how one can use statistical thermodynamics for our desired thermodynamical properties also. But we will start with the probability problems, simple ones. A box contains 3 marbles, one red, one green and one blue. So, I will just annotate with that color, one red, three marble, one red, one green and one blue. Consider an experiment. So, this is a box, I should have drawn the black box. Consider an experiment that consists of taking one marble from the box and then replacing it in the box and drawing a second marble from the box. Describe the sample space. So, in our sample space, the first marble can be either red, green or blue, and since we are replacing them back, so again the box contains all the 3 marbles. So, that means for red it can be either red, green or blue. For the green it can be either red, green or blue, and for this one also it can be either red, green or blue. So, now if I correspond to sample space, then this is one of the sample space red red, red green. So, if I write down all of them, it will be red red, red green, red blue, green red, green green, green blue, blue red, blue green and blue blue. This will be the corresponding sample space, because these are the all possibilities of outcome of the experiment that is described in this particular problem. Repeat when the second marble is drawn without replacing the first marble. Now, we say that okay, if I do that, then I am not going to get the first marble. Now, what will be the situation? Let us say if I take the red marble first, in that case second time either I can get a green marble or I can get a blue marble. These are the 2 possibilities in the sample space. Let us say I had the green marble first, then I can either take the red marble next time or I can take a blue marble next time. Let us say I took the blue marble first, then second time I could have taken either red marble or either green marble. So, you can see in the second case the number of points in the sample space is smaller, because it is done without replacement, whereas the first one is done with replacement. Okay, now, we go to the next problem. 2 green balls and 1 red ball are drawn from a barrel without replacement. So, now I have 2 green ball and 1 red. There are 3 balls are drawn from the barrel without replacement. Compute the probabilities PRG of drawing 1 red and 1 green ball in either order, which means I can either take a red one and then a green one, or a green one and then a red one. So, if I now do that, so here we see this in either order means we can either take red one first and then green one, or green one first and then red one. We can calculate the probabilities. So, the PRG therefore will be PR multiplied by PG, which is an AND probability, plus PG multiplied by PR. So, either order. So, R followed by G and G followed by R. Now, what is the probability of drawing a R? That is 1 by 3. Once I draw the red, I have the full probabilities of getting the green, which is 2 by 2. Now, if I take the green first, which has 2 by 3 probability, after that I have 1 green and 1 red left. So, the red will be 1 by 2. So, now it is giving me 1 by 3 plus 1 by 3, which is 2 by 3. Compute the probability of PGG. So, this is a problem. Second problem B, compute the probability GG for drawing 2 green ball. So, 2 green ball means first green has to be green and second also has to be green. So, PGG we will use only AND probability because there is nothing OR taking place. So, first one will be 2 by 3 probability and second one I will be left with one green and one red only, and that will be 1 by 2. So, PGG will be probability 1 by 3. So, you see that when I am talking about 1 and then 1 and then 1, 1 and then. So, AND is there. So, there is a multiplication, and if I have OR possibilities like for example, here, and that was a possibility where I had OR function. So, this is the OR probability which is add up, and this is the AND probability which multiplies. Okay, coming back to the third problem, how many arrangements are there of 15 indistinguishable lattice gas particles distributed on 20 sites? So, this problem I can draw like this. There are sites So, these sites are kind of distinguishable sites. I can name them as 1, 2, 3, 4, 5, 6, 7, 8, and there are 15 indistinguishable 15 indistinguishable lattice gas particles. So, the gas particles are indistinguishable, and the thing is that one lattice points will have only one particle. So, it is not that I can put multiple particles there. So, whenever I can do I cannot do that. So, as I tell you that for indistinguishable particles in distinguishable cells, the distribution will follow the star bar problem. However, if you can put only one particle in one lattice sites, then it is basically how many ways you can choose those lattice sites in order to put the particle, that becomes the question. So, I have 15 such particle, and I have in the first case 20 sites. So, I have to choose now 15 out of 20 sites to put the particle, that is it, that is the only problem. So, that means out of 20 sites I have to choose 15 of them to put the particles. So, the number of ways will be 20 C 15. In the second case I have 16 sites left. So, 16 C 15 and that is nothing but 16 factorial by 15 factorial and 1 factorial, which is going to give us 16, and in the case of C it is 15 C 15 going to give us 1, and in case of 20 it will be 20 factorial by 15 factorial and 5 factorial, which is going to give me 20 into 19 into 18 into 16 17 into 16 divided by 5 into 4 into 3 into 2 into 1. We are going to do that using a calculator, and that will tell us what the value is. 20 C 15, 15,504. That is the number. So, you see, as the number of lattice sites are increasing, the number of possibilities increases, and therefore, again entropy increases. This is an equivalent way of saying that there is a free space available for particles to expand. Okay, going to the next problem. A scientist has constructed a secret peptide to carry a message. You know only the composition of the peptide, which is 6 amino acid long. It contains 1 serine, 1 threonine, 1 cytosine, 1 arginine and 2 glutamase. What is the probability that the sequence secret will occur by chance? So, now we have to see that how many possible words one can make with that. So, the number of possible words that you can make is that we can take any of the 6 letters and put it in my first place of the word, and then any of the second letter, there will be 5 letters left, then there will be 3 letters left, 2 letters left, 1 letter left. However, you have to know that there are 2 E's. So, interchanging those 2 E's will actually give the same word. So, I have to divide by the factorial 2. So, total possibilities, total possible words equal to 6 factorial by 2 factorial, which is 720 by 2, which is 360. Out of this, there is only one word which is secret. So, the probability is equal to 1 by 360. So, note that in the secret these two exchanging these 2 E's has already been taken into account for the total probability, a total number of ways. So, they are exchanging these 2 is not giving rise to any new word. that has been already taken into account. Now, we go to the next problem, problem 5. Assume that 4 bases A, C, T, G occur with equal likelihood in a DNA sequence. That means, it can come anywhere. So, out of these 4 anything can come like A, C, G, T, C, whatever it can come, and that is how the DNA is made, right. So, now what is the probability of finding the sequence, a very particular sequence through the random choice? Now, you see how many ways you can get, what is the probability of getting a in the first place? So, there are 4 possible sequences and you are asking for just one particular one. So, that will be 1 by 4. What will be the second one? Again 1 by 4. What is the third one? Is again 1 by 4. So, like that when you go, the answer is that 1 by 4 to the power n, which is the length of the DNA. In this particular case, it is 1 by 4 to the power 9. So, that is the probability of getting that particular sequence. Problem B also the same thing, although it is same sequence A, but each one is independent of the previous one. Therefore, for the B also, since there are 9 letters are there and each letter has 1 by 4, the answer will be 1 by 4 to the power 9. Now, in case of C, what is the probability of finding any sequence that has 4 A's, 2 T's, 2 G and 1 C? Now, first we will see how many that kind of sequences are possible. In order to see that, we know that this in the 9 letter sequence, it can A can come, any of these 9 can come in the first place and then 8 will be remaining, then 8 will come in the second place and things like that. So, there will be 9 factorial possibilities, but we know that there are 4 A's which are common and 2 G's are common and 2 T's are common and 1 C is common. So, this is the number of sequences that we can create, and we already know from the previous examples that any such 9 letter sequence has a probability of 1 by 4 to the power 9. So, this is the answer to this particular question, is that it is 9 factorial by 4 factorial, 2 factorial, 2 factorial into 1 by 4 to the power 9. We will just calculate that and see what we are getting out of that. 9 factorial divided by 4 factorial into 2 factorial into 2 factorial multiplied by 1 divided by 4. So, we are getting as 0.014 as the probability of having such sequences. Let us come to problem number 7, which is called Monty Hall problem. So, this problem is like this. Long back there was a game show, the host was called Monty, host name was Monty Hall. So, he would tell a person to choose a particular door. Behind 2 doors there are 2 goats and behind 1 door there is a car. So, let us say you will choose a particular door, let us say you will choose door C. Then Monty will open another door behind which there is a goat. Monty knows where all the doors are. So, Monty will open a door behind which there is a goat, and after you look at the goat, Monty will ask you again, do you want to stick to your choice C or you want to change it to B? Let us say the Monty opens gate number A. So, you have chosen gate number C, all the doors were closed before and Monty opens gate number A. So, now the car is either behind C or behind B. Now, Monty will ask again that do you want to switch your change to B or you want to stick to C? What should you do? You want to change? Huh? Why do you want to change? In A there is a goat for sure, but in behind B there can be a car, or behind C also there could be a car. If you switch and if the car is behind C, then you will not get it.
There is an equal probability in both cases.
So, okay, so you think there is an equal probability in both cases? Okay, so that is what the thing is that people initially were very confused at what to do, means maybe it is equal, maybe it is random, but eventually it turns out that it is actually not a random choice. There is a definitely higher probability for switching, you must switch. The reason is this. So, reason very simply, first reason is that when the all doors are closed, the probability that the car is behind C is 1 by 3, 1 by 3 and 1 by 3. The probability that the car is behind C is 1 by 3, right. So, that means probability that between this two doors the car is there is 2 by 3. So, all are 1 by 3 initially, but then you have chosen that the car is behind C with the probability 1 by 3. That means, the fact that the car is there in B and A is 2 by 3, B and A, and now Monty opens the door A, that means definitely car is not there. So, which means this 2 by 3 now goes to only B. Is it okay? Okay, so I will explain once. So, let us say initially when you do not have all the doors were closed, then the probability that the car will be behind any door A, B, C is 1 by 3, which means that let us say you have chosen C, this is B and this is A. That means, the combined probability of B and A is 2 by 3 for the car to be there, combined probability, or it can be either in B or in C. So, it is 2 by 3 because it is the odd probability, right. Now, Monty opens the door for A and A for sure does not have a car, which means the probability that B has car is 2 by 3 initially when the doors were not opened, but the fact that Monty knows which door has a goat and he opens only that door changes the probability. Now, I will explain here. So, let us say you are choosing, we are calculating here all possibilities. So, it will make it clear. Let us say you choose door number 1 and the car is also behind 1. So, if the door number 1, let us say you choose that door A, door number some door where there is a car, let us say the car is here only, you chose C and the car is there. So, then Monty will open any of the other two doors, and then if you stay you will win, if you switch you will lose, correct. Let us say you choose 1 and the car is in behind door number 2. Then Monty will open any of the two doors, Monty will open precisely one particular door which is 3. Okay. Let us show all the possibilities once more. Actually, I should not switch between A, B, C and 1, 2, 3. So, let us do that 1, 2, 3 way. So, let us say you choose door number 1 and the car is behind door number 1. Monty will open any of the other two because other two have goats now, and if you stay you will win and if you switch you will lose. Okay. That means, you should not switch in that case. Let us say you choose 1 and the car is behind 2, they are all equal probability, right. That time if you switch you will win, right. Let us say the car is behind 3, door number 3, if you switch you will win, right. So, you see if you choose 1, then 2 times you win if you switch and 1 time you will lose. Similarly, the same thing is true for if you choose door number 2, there also 2 times if you will win if you switch and 1 time you will lose. Similarly, if you choose 3, 2 times you will win and 1 time you will lose if you switch. So, if you switch you will win more often than if you do not switch. So, probabilistically it is always advantageous to switch.
And if you take like 100 doors, then should
Yeah.
switch.
So, let us talk about 100 doors. So, there are 100 doors and you choose one of the 100. What is the probability that the car will be there is 1 by 100, right. And Monty opens all 98 doors, he knows the goats where the goats are. Now, should you switch or should you not switch? Because initially
98 doors, then
we should switch. So, it becomes easier to think about when there are 100 doors, only with 3 doors it becomes not so clear. So, initially when you chose, your probability was 1 by 100, and altogether 99 doors had the probability the car is there 99 by 100. Now, since Monty opened all the doors, the car is there in one other door is 99 by 100, because that time also it was 99 by 100, now also it is 99 by 100, except that you now know all the other doors have goats. So, the fact that, see, initially you chose the door C, which has 1 by 3 probability. So, B C combined was 2 by 3 probability, is not it? Now, you know that C does not have that, I say B and C. So, you chose door number A, and B and C had the 2 by 3 probability of having the car, and you know now that C does not have the car. So, B will have 2 by 3 probability of car, that means you should switch. Okay. That is a famous Monty Hall problem.
So one more thing, if you know the C doesn't have the car, so we have the A and B. So to that point, we can think about that maybe the equal probability A and B.
No, the thing is that, see, if you, so the initially why the probability was 1 by 3, because it was totally a random choice, right. That is why it is 1 by 3, 1 by 3, 1 by 3. Now, whenever somebody opens a door, your sample space immediately reduces. So, you had that 2 by 3 probability of in the 2 doors. Now, one is removing 1 possibilities for you. So, which becomes much more, it is not random anymore. See, Monty knows that which door has the goat. So, it is not random. If Monty opened the door randomly, then it would be a case, but Monty knowing that he is going to open only the door with the goat is no longer random. So, all probabilities collapses to one particular door. Okay. It is a very famous problem, and in fact, this table shows very clearly that all the possibilities. If you just look at the table, whatever you do, 2 cases if you switch, you will win, whatever you do, and 1 case you will lose out of the 3, and in 99 case you will see 99 by 100 it will be the other door.